In this video, we're going to explore the fascinating world of query processing, focusing specifically on Transact SQL, or T-SQL for short. Now, T-SQL is the primary language we use to communicate with Microsoft SQL Server and Azure SQL databases. Understanding how queries are processed is super important because it empowers you to write more efficient and effective SQL commands. So, let's dive right in. First, think of T-SQL as the bridge between you and the data you want to manipulate. By getting a grasp of how these queries work, you'll be able to extract the information you need, update records, and run complex analytics with greater ease. Remember, every query you write goes through a process of parsing, optimizing, and then executing, and each of these steps has a significant impact on performance. So it's all about efficiency here. By the end of this session, you'll feel much more confident in your querying abilities, and trust me, that'll make working with SQL databases so much more enjoyable. All right, ready? Let's jump into the details. Now, let's take a look at a basic SQL query that retrieves specific information from our employees table. This query is designed to fetch the first and last names of all employees working in the sales department. To start, we utilize the select statement. This is where we specify the columns we're interested in, first name and last name, followed by the from clause that indicates our data source, which is the employees table. Now, it's important to note that the query is filtered with the where clause. This ensures that we only get those entries where the department equals sales. This conditional filter is crucial for narrowing down results to just the relevant subset of data. By executing this query, we let SQL Server parse the statement, verify its syntax, and check if the specified columns and table exist. After that, SQL Server processes the command to retrieve the desired information efficiently. Understanding this fundamental query structure really lays the groundwork for crafting more complex SQL statements in your future database interactions. Now, let's dive into implementing the command that'll help us generate and view the execution plan for our earlier query. By enabling the Show Plan XML option, SQL Server won't actually execute the query. Instead, it will present an XML representation of the execution plan. This approach allows us to really see how SQL Server plans to access and retrieve data from the employees table, specifically those lovely folks in the sales department. Once we have Show Plan XML turned on, you can run a simple select statement that retrieves the first name and last name from the employees table where the department is sales. It's pretty much like our earlier example, but this time we're really focused on understanding the execution plan SQL Server comes up with based on the existing indexes and row statistics, rather than just fetching actual results. Now, once we wrap this up, we'll disable the Show Plan XML setting to return to our normal query execution state. Reviewing this execution plan is crucial as it uncovers insights into the efficiency of our query. This way, we can make informed decisions about any optimizations and improvements we might need to consider. The accompanying figure, titled Understanding SQL Query Processing Stages, displays a bar chart with 4 distinct stages on the x-axis: parsing, compilation, optimization, and execution, and their measured durations on the y-axis in milliseconds. The bars are color-coded: green for parsing, blue for compilation, amber for optimization, and red for execution. And they're annotated with exact numeric values on top. Parsing takes 50 milliseconds, compilation is at 120 milliseconds, optimization comes in at 80 milliseconds, and execution, the longest stage, takes 150 milliseconds. Now, from these numbers, we can observe some clear patterns. Execution consumes the most time at 150 milliseconds, which is about 37.5% of the total 400 milliseconds. After that, we see compilation at 120 milliseconds, making up 30%. Optimization contributes a solid 80 milliseconds, or 20%, while parsing, the smallest segment, comes in at 50 milliseconds, only 12.5%. This distribution highlights something quite interesting. A whopping 67.5% of processing time is spent on compilation and execution combined. So, if we're looking to improve overall query performance, it makes sense to focus on reducing execution time using better indexing, updated statistics, or optimized plan choices. And for the compilation stage, streamlining could involve simplifying complex queries or reusing cached plans, which can help a lot. Even though optimization is smaller in duration, it still plays a meaningful role, and it can be influenced by keeping statistics up to date or rewriting certain queries for efficiency. The annotations in the chart make it straightforward to see which stages will yield the greatest benefits when optimized. So there you go. The stage labels directly map to our discussion of parsing, planning, optimization, and execution in this lesson. Now, let's see how we can implement an index on the department column of our employees table, which is essential for improving the performance of queries that filter by this field. The syntax is pretty straightforward. It starts with the create index statement, followed by the name we want to give our index. In this case, let's name it IDX Department. This name is designed to be descriptive, making it easier for us and anyone else looking at it to understand it at a glance. Next, we specify the table we're working with. In this instance, that would be employees. And then we indicate the column we want to index, which is, of course, department. So, when we execute this command, SQL Server creates a structured index specifically for that column. This allows SQL Server to quickly locate the relevant rows whenever we run queries that filter based on the department, without having to sift through each record one by one. However, it's crucial to keep in mind that while indexes significantly enhance read operations, they can also introduce some overhead for write operations, since the database needs to update the index every time records are inserted, updated, or deleted. Therefore, balancing the use of indexes according to your application's needs is key to optimizing performance and ensuring efficiency in your database management. Next, we will write a query to count the number of employees in a specific department, in this case, the sales department. The SQL command begins with the select statement, which is used to specify the data we want to retrieve, in this instance, the total number of employees. By using count*, we instruct SQL Server to count all records that match our criteria, ensuring that even if the department has no employees, we'll still have a clear indication of the count. Following this, we specify the table we are querying from, the employees table. This is where SQL Server will search for the relevant records. Now, the where clause is crucial here, as it filters the data to include only those employees whose department matches sales. This powerful feature of SQL allows us to narrow down potentially large data sets to specific groups, making our query both efficient and effective. Using this approach, if an index exists on the department column, SQL Server can quickly retrieve the necessary counts, without needing a full table scan, vastly improving performance and demonstrating the dynamic optimization capabilities of SQL Server during query execution. Now, let's see how we can implement an inner join to combine data from two related tables. In this example, we are joining the employees table with the departments table. Our goal here is to retrieve each employee's first and last names, along with the name of the department they belong to. So, to achieve this, we'll use the inner join clause, which matches records from both tables based on a common field. In this case, that's department ID. When the department ID from the employees table matches the department ID in the departments table, Aha! SQL Server merges those rows into a single result set. Now, it's also important to note that SQL Server evaluates the statistics of the tables involved to determine the most efficient way to execute this join. It considers the size and distribution of the data, which is quite fascinating, right? By executing this query, you'll gain a clear view of employees and their respective departments in one cohesive output. This illustrates how relational databases effectively use joins to extract meaningful data from multiple sources. It really demonstrates a fundamental aspect of query optimization by utilizing relationships between tables for efficient data retrieval. Now, let's take a look at how subqueries can enhance our SQL queries by allowing us to nest one query within another. In the following example, we'll retrieve the first and last names of employees whose department ID matches a specific condition obtained from another query. So, here we go. The inner query fetches the department ID from the departments table where the department name is sales. This efficiently creates a filtered list of department IDs tied to the sales department. Now, the outer query then uses this list to select employee names from the employees table that correspond to those department IDs. This method allows for a clear separation of logic. It's like isolating the logic for identifying the relevant department while still extracting the necessary employee information. However, while this approach definitely improves readability, it's important to remember that performance might take a hit, especially in larger datasets. So, it's often recommended as a best practice to consider transforming subqueries into joins when possible. This can lead to more efficient query execution in T-SQL. Now, let's see how we can implement a set-based operation to increase the salary of all employees in the sales department. The SQL command begins with the update statement, which is used to modify existing records in a table. In this case, we're targeting the employees table, where we'll filter for specific records based on the department column. So, by specifying set salary equals salary times 1.10, we're instructing the database to take the current salary of each employee in the sales department and increase it by 10%. This operation is efficient because, unlike procedural code that loops through each record and updates them individually, this command processes the entire set of qualifying records in one go. The where department equals sales clause ensures that only the employees in that specific department are affected. This bulk operation minimizes overhead, showcases the power of T-SQL's set-based capabilities, and leads to a performance boost compared to handling row-by-row updates. By leveraging this method, we're ensuring that our data manipulation is both efficient and effective. Now, let's explore how we can implement error handling and transaction control in T-SQL, ensuring our database operations maintain integrity and reliability. We start with the try block, where we kick off a transaction to update employee salaries by 10% for those in the sales department. This transaction envelops our update operation, treating all changes as a single unit of work. If everything runs smoothly, we can confidently commit the transaction, which permanently applies the changes made. However, as we know, real life can be a bit unpredictable. Things don't always go as planned. Errors can pop up for various reasons, like network failures or deadlocks. This is where the catch block becomes essential. If an error happens during the execution within the try block, control smoothly transitions to the catch block, where we roll back the transaction. This crucial action undoes any changes made during the transaction, reverting the database to its previous stable state. Plus, the code prints out the error message, giving you valuable feedback to help diagnose the issue. This structured approach to error handling is absolutely vital for maintaining data integrity during those critical operations. Now, let's dive into a practical example that shows how to increase the salaries for employees in a specific department. Yep, we're zeroing in on our sales team. So, we begin with the update statement, which we'll use to modify some existing records in our employees table. The magic happens in the set clause, where we get to specify just how we want to change things up. In this case, we're giving each employee a nice little 10% raise. And how do we do that? Simple. We multiply their current salary by 1.10. Now, to make sure we're only updating the right folks, we'll add a where clause. This narrows down our focus just to those employees in the sales department. With this precise targeting, we're not only boosting efficiency by avoiding unnecessary changes, but also keeping the integrity of our data intact. Using these set-based operations really showcases the strength of T-SQL, allowing us to handle bulk actions with ease, meaning the database can process all these changes in one go, rather than having to loop through each employee one by one. By embracing this set-based logic, we can really supercharge performance, especially when we're working with larger datasets. Understanding query processing in T-SQL allows you to write better, optimized SQL commands that effectively communicate with your databases. For anyone looking to advance their SQL skills, mastering these concepts is crucial. From parsing to execution to optimization, each step in processing your queries is essential to ensure that your database performs at its peak. Embrace these principles and apply them to your work, and you'll find yourself not just writing SQL, but becoming a maestro in data manipulation. Thank you for watching, and happy querying!